So we've discussed line integrals in general. This is the generalization of a single integral that we learned in Calc 1. We have a function of 2 or even 3 variables, and we're integrating it now over a curve in 2D or 3D space. We have 3 versions of that. We can integrate with respect to arc length, which is kind of the natural thing. We're weighting the values of the function by the arc length of the actual curve that we're following. But we had 2 other versions, which is we could just weight it by the horizontal length or just the vertical length. Yeah, so those were the 3 varieties of line integrals. We also extended this to vector fields. The original line integrals are just regular real-valued functions. But if we have a vector field, we can do this kind of line integral. The vector field dot it with dr. And one way to write that is just to break that up into the components of f, which we always call p and q. And we integrate p dx and then q dy, and we add them. And by the way, we learned how to actually evaluate these directly. In all cases, you can turn them into a single Calc 1 integral. All right, but then we learned that there is a fundamental theorem which says that for the vector field situation, if your vector field happens to be the gradient of a function, then your line integral is just that function evaluated at the end, evaluated at the start of your curve, and you subtract them. So your real valued function evaluated at the end minus the real value function evaluated at the beginning. And that is true, again, if your vector field happens to be a conservative vector field, happens to be the gradient of some real valued function little f. Great. So next thing I want to ask is, well, what if the curve is a closed curve? And actually, you've already read a little bit about this as well. If your vector field happens to be conservative, happens to be the gradient of a little f, then, and you're integrating over a closed curve that comes back, basically a loop, it comes back on itself, well, then the end and the start are, of course, the same point, and so this would be 0 every time. So conservative vector fields, if you integrate them .dr over a closed curve, you're going to get 0. However, if your vector field is not conservative, it doesn't have to be 0. It could just by luck, but it doesn't have to be. So yeah, if you have a non-conservative vector field, the integral is not necessarily 0, and you can attempt to just work it out from first principles if you have a parameterization of your curve. Okay, but we are going to have another sort of fundamental theorem of calculus type theorem for this situation. Actually, for both, although this one is obviously already figured out for us. There's another theorem that we can talk about that deals with line integrals of a vector field when you go around a closed curve. Okay, and this is called Green's theorem. So again, the setup is the following. We want to compute a line integral of a vector field .dr over a closed curve C. And Green's theorem says that that integral is equal to the following. It is equal to a double integral over a region that I'll call D. And this region D is actually the inside, the two-dimensional inside the interior of the closed curve C. So it's the region, it's the interior where C is the boundary. So a double integral of that over that region of the derivative of q with respect to x minus the derivative of p with respect to y. And this is a regular double integral that we've dealt with in multivariable calculus. Now, before I go any further talking about using this, let me say that there's a small asterisk, a small technical detail that I have to point out, which is for what I've written to be true, C, you have to be going around C. The integral that you're doing or over C has to be going in what's called a positively oriented direction. Because you can go around this boundary in two ways. And of course, if you go around one way, you have one answer. If you go around the other way, you'll get the negative of that number. So it matters which way you're going around. So which of the two ways is equal to this double integral? Well, it's the one that goes around in the positive orientation. Simple way to think about that is it's counterclockwise. In real simple cases, that's what we mean, counterclockwise. But sometimes the shape can be very weird, and what is counterclockwise is not obvious. And so let me just say that positively oriented, the official definition means as you go around, the D is always on your left. So you see, if we go around, and this one we can say counterclockwise. If we go around counterclockwise, if you imagine actually traveling that route, the D, the interior that we're talking about, would always be on our left side. So D always on left as you traverse C. Okay, so if you happen to be doing an integral where you're going the other way, okay, well then you can use Green's theorem and you just have a negative. It would just be the negative of this double integral. Okay, but we will pose this assuming that we're going around in the positively oriented direction, and then it is equal to just the double integral without a negative sign. Okay. Now, I want to say that this is a type of a fundamental theorem of calculus. A fundamental theorem to figure out integrals is what I mean by that is always of the form of we're connecting one integral with an integral or something like an integral on its boundary. So clearly, in this case, we start it with the boundary, and we're saying it's the same as this double integral, and that the thing we're integrating in on the non-boundary part is some kind of a derivative. So sorry, that was poorly worded, but that's the basics of anything that we might consider a fundamental theorem for integrals, is that kind of a setup. But anyway, whether that's clear or not, we'll move forward. Yeah, so this makes a connection between line integrals around closed curves and double integrals. Now let me just say that this connection between these two things can be exploited in either direction. I've given it to you assuming we start it with a line integral on a closed curve, and I've said this is a way to figure that out. And yes, in some cases the line integral, to try to figure that out directly might be difficult, but doing the double integral might be easier, particularly because when you do these derivatives, the thing you're integrating might get considerably simpler, and that's why this double integral might be more feasible. However, it might go the other way. It might be that you're trying to figure out a double integral, and then you can, and it might be difficult for whatever reason, but you might be able to use Green's theorem to turn it into a line integral. Now that was at first a little bit more difficult because you have to figure out your P and your Q. You kind of have to anti-differentiate these two guys and get back to that. But then if you can, and if you can then integrate around the boundary of your D, then you could evaluate it that way. So in some cases it's easier to turn it from line integral to double integral, and in some cases it's easier to go from double integral to line integral. So Green's theorem works in both directions. Let's look at an example. Here's a line integral that we would like to compute. And we're integrating, the line integral is over this curve, and this curve is simply the radius 1 circle centered at the origin, going counterclockwise. Now, if we were to do this directly, right, we would have to have a parameterization for this curve, and that would be not too bad. That would be cosine t, x equals cosine t, y equals sine t, where t runs from 0 to 2 pi. That's the simplest parameterization of a circle. Okay, but you can see that when we plug those in, we'll have a cosine t squared, we'll have a sine t cubed, and so on. We'll have squares and cubes of trig functions. Also, the dx, right? Remember, this gets replaced by dx, dt, and then dt. So we'll have another trig function when we take the derivative, right? Like a minus sign here. And then same thing here. We'll have a cosine t right there. So we'll just have lots of trig functions and powers of trig functions all over the place. And actually that is doable, but let's try to use Green's theorem and see what it gives us in this case. So to do Green's theorem, our D is the interior. So we can turn this, oh, and by the way, this is positively oriented, right? We're going around counterclockwise. If we go around, the inside is on our left. All right, so we can turn this into a double integral of, now this is our P and this is our Q. And Green's theorem says it's dq dx. So the derivative of this guy, dx. Now, notice how this gets simpler. The y squared goes away when you take the derivative with respect to x, and we'll get 3x squared. Okay, minus, and then it's dp dy. So then the x squared goes away, and it'll be minus 3y squared. So minus a minus 3y squared. And then we integrate this dA over this circle. Okay, so far so good. Now, can we do this? We can. To do this double integral, because it's over a circle, and this is something that you got a little bit used to in multivariable calculus, doing double integrals over circles, polar coordinates are often going to make your life easier. So we replace dA with r dr d theta. Our theta goes from 0 to 2 pi, so we have a full circle. Our r goes from 0 to 1 because it was a radius 1 circle. And then we just have to convert what's inside here into polar coordinates. But this again is going to help us because, well, we can factor out a 3 first of all. And then what's left is x squared plus y squared. But x squared plus y squared in polar coordinates is r squared. And so in the end we have 0 to 2 pi, 0 to 1, 3r cubed dr d theta. Do the inside integral. That'll be 3/4 r to the 4th. Evaluate at 0 to 1. Plug in the 1, plug in the 0. You can see we'll just get 3/4 there. And then we're just integrating a constant from 0 to 2 pi, so that'll just be the 3/4 times 2 pi. So I think we're going to get 3 pi over 2. And that will be the answer. And that was easier than trying to wrestle with all these sines and cosines and trying to do those antiderivatives back here. Okay, so there's an example of using Green's theorem to do a line integral by turning it into a double integral.